Okay, so in the previous chapter, we had discussed about the power factor and how the power factor is present in the AC circuits. Also the effects of capacitive and inductive loads on the power factor. So basically in an electrical transmission, having a non-unity power factor is quite common. However, EVs do not want to use a non-unity power factor and would implement certain methods to make it a unity power factor at all times. So in this chapter, we will have a look at the topologies which are implemented in the onboard chargers to ensure that the power factor is close to unity and to ensure there is maximum efficiency and maximum power. So as part of that, we can have a look at one of the topology which is called as a Totempole topology. So there are also certain other topologies like double boost and so on, but the most contemporary research focus is revolving around the totem pole based, mainly because of the advantages that it offers. So in a typical double boost topology, it's a two-stage conversion of the power electronics. However, in totem pole, we have a single stage. So what does it mean is, so the power factor correction as well as the correction from AC to DC happens in a single stage. So that's the advantage of totem pole. So the name comes from the fact that we have just two legs standing like this on the screen, and that is all. So we have a very simplistic power electronic converter in terms of totem pole technology. So let's have a look on what generally happens in a power factor correction. So going back to the basics from the previous chapter, so what does it mean to have a unity power factor? So if we have a voltage which is of this, and as long as we have a current which is following exactly the voltage, so if we have the black one and the current, it's exactly following the voltage, so then we say the power factor is equals to 1. Yeah, so this is our target. So how do we achieve it? So that's how that's all in the control of this particular power electronic circuit. So if you have a look at so the current which is flowing through the inductor, right? So our target is the current flowing through the inductor must follow the voltage source. So if this is my voltage from the AC terminals, I want to see my inductor following exactly the same voltage. So how does it happen? So there needs to be a certain logic which is controlling it. So we typically have something called as a PID or a PI loop, which ensures that based on the reference voltage of the AC mains, the current is always flowing in the similar manner. So what essentially we will see is it's not the current will not be exactly smooth like this. So when we are switching multiple times, so we see that it is switching like this. Yeah. So it's going to be something of this sort. And how good or the ripple around here is going to depend on how good the PI loop is. So modulating the PI loop is quite important. So what should be the frequency of this switching is very, very important as well. But more or less, the PI control is what decides how good the output is going to be. So now, how do we make this work? So let's have this as the positive half, and let's say this is my negative. Okay, so now, so we get into the switching of this particular power electronics device. So let's go back to the drawing. Yeah, so we have, let's say, the current passing through the inductor, which is through this basically. Yeah. So when we switch S2 and S1, so there is a certain way in which the MOSFETs are switched. So for example, S2, typically we say that it gets, let's say, a duty of T, then S1 gets exactly the opposite, so the 1 minus T. Yeah, so there is of course a dead time and so on, which we will not really focus on. Going further, so when we have S2 switched on, so in the positive half cycle, so we will see that the current is going through this, it's going through this, and then you see the diode D2 is forward biased, and then it goes back into the source. So which means when in the positive half cycle, so if S2 is switched, you will have just a circulating current in the inductor. So nothing goes out onto the DC side or onto the ultimate load side. So what essentially happens is on the DC side, yeah, so there's no question of power factors or anything. So voltage and the current are in sync, right? So all that we need to ensure is the current through the inductor is in sync with the voltage, right? So for me in the logic, the VAC should be exactly in phase with the IL, or the other way around. The IL should be exactly in phase with the VAC. And similarly, when we have the switch S1, which is turned on, so we will have the current going through this. So we see the diode is now reverse bias, which means it has to enter through the load, or yeah, in this case we have a capacitor, which is the DC link capacitor, and then through the diode, it makes its way back. Right. So we have two different ways in which the current is either charged or discharged. So in the first picture here, the inductor is always charging. In the second picture here, the inductor can discharge into the load. Right, and similarly in the negative half, so what you see on the S2 and the S1 will get inverted. So you will get in the negative half, S1 will get such a thing and S2 will get such a thing. Okay, so now how does it help, right? So we go into the control logic. So what do we do is we have a PI controller, right? So to which we have, let's say, we feed in the reference voltage. We feed back what is the current through the inductor as a V reference. So there will be a gain block. So there will be a gain block, and then we kind of feed. So whatever is the error is going into the PI block, and the PI block is going to tell me what is going to be the duty, which switch is supposed to be switched, Q1, Q2, and for how much of a duty. So right, this is what gives me, let's say, the plant model of it, and then I have a current. So we have a complete closed loop system wherein we are telling, in a sense, that the difference between the Vref and the current should be none, right? So that essentially does what we want. So we have an AC circuit, and we have an AC voltage, and we have the current which is exactly following it. So just imagine if the current is going negative, so something like this, just an example. So what we want is the inductor current to go up here, right? Or in other ways, if the inductor current is here, we want it to come down to here. So what can we make of from the previous diagrams is that if you want the inductor current to rise, we need to switch S2, right? So in this case, we switch S2. And if you want the inductor current to fall, so we switch S1, right? So that is how things work. So but yeah, this is a huge deviation which I've mentioned, but we have a very good PI controller and a very high frequency. So this happens at a very minuscule level. So it's going to have a few milli or microampere deviations happening here. So which means the current sensor should be, yeah, really of high precision. So it's going to happen something like this. So essentially, how much of this, let's say, overshoot or undershoot happens is depending upon the PI. So if you have a greater integral, so basically what an integral does, it is basically integrating all of the errors. So you can have a very good eventual stability, right, with a high integral constant, but however it can cause an initial overshoot and undershoot. So the tuning of the P and I parameters are going to be extremely crucial in getting a good result. So this is the fundamental of how the totem pole based PFC converter works, and in the next chapter we will have the practical MATLAB simulation.